Swayam Prabha. Digital India. Educated India.
Welcome to the 24th lecture in Mechanics of Materials. The last lecture we saw how to solve a simply supported beam subjected to a 2-point loading to find the bending moment, shear force, reflected shape, the slope of the reflected shape, and design the cross section such that the maximum compressive stress and maximum tensile stress are within limits. In this lecture we look at how to find the stresses and deflection in inhomogeneous beams. Okay. Basically, till now we have assumed that the beam is homogeneous, meaning that it is made of the same material throughout the cross section. What we are going to, and we derived that bending equation that minus sigma xx by y minus y naught is equal to mz by iz is equal to E times z square delta y by dx square. Okay, but this E is the Young's modulus, meaning the material shows a similar response in tension and compression, and that it is made of the same material. The entire cross section is made of the same material with a Young's modulus C characterizing the sustained response. Okay. Now, what we are going to do is, if I look at the cross section of this beam, I am going to say that the cross section of the beam is made of two materials, say wood, and this material is say steel. Now, how do you analyze such a cross section is what we are going to see. Since there is a different Young's modulus for wood, which we will denote it by EW, and a different Young's modulus for steel, which we will denote it by EST, you can't use a single value of Young's modulus for the entire cross section as such. Okay. So, you have to revisit the derivation that we did for this, obtaining this equation to account for the fact that the cross section is not homogeneous. Okay. So, if you recollect, in the initial lecture of the beams, we said that the displacement of the beam u is given by minus y naught into d delta y by dx Ex plus delta of y as a function of x Ey, right. This was the displacement field that we got by assuming that the plane section remained plane and normal to the neutral axis of the beam. Okay. Sections were initially normal to the neutral axis of the beam remains normal to the neutral axis of the beam after deformation. Okay. So, based on that assumption we got this as the displacement field. Okay. From here we computed the epsilon xx strain as minus y naught d square delta y by dx square, right. Okay. Even when the beam is inhomogeneous, we assume that this is the displacement field and this is the strain field. Okay. Meaning we assume still plane sections normal to the axis of the beam remain plane and normal to its axis. Okay. So, basically this assumption, which is called as the Euler-Bernoulli assumption, holds even for inhomogeneous beam. This assumption is called as Euler-Bernoulli assumption or plane section remain plane assumption. Another name for this is plane sections remain plane. Okay. Okay. Now, then if the stress is given by this expression in here, then the sigma xx strain is given by the expression in here, the sigma xx stress would be given by E as a function of y into y minus y naught d square delta y by dx square, right. Okay. And then we employed the two equilibrium equations, namely integral sigma xx dAx Ax has to be equal to 0, that is no net axial forces applied in the cross section, and the fact that sigma xx into y minus y naught dAx integrated over the cross section area must be equal to the applied moment mz at that cross sectional location. Okay. So, now if you apply this, when E was a constant, we pulled the Young's modulus outside the integration, saying that it is a constant. Now you can't do that, so let us find out what restriction these equations place. Okay. So now you have E of y into y minus y naught dAx Ax has to be 0. This will imply that y naught is integral E of y into y dAx Ax divided by integral E of y dAx. Okay. Now then you are substituting for sigma xx in the second equation, you have E of y into y minus y naught whole square dAx into d square delta y by dx square. I left the negative sign for the stress here. So with the negative sign in there must be equal to your mz moment there. Okay. So now what happens, I can't pull the E outside, so d square delta y by dx square is mz divided by integral E of y into y minus y naught whole square dAx Ax. Okay. Now substituting this in the stress expression, what we get is, so combining this is the equation to find y naught and this is the equation to find d square delta y by dx square. Okay. So your stress expression becomes sigma xx by E of y into y minus y naught is d square delta y by dx square, which will be equal to mz divided by integral E of y minus y naught whole square dAx Ax. Okay. So now this is a general bending equation when the beam is inhomogeneous. Okay. This is a general bending equation when the beam is inhomogeneous. Here the y need not be a function of y alone, E can be a function of z also, in which case I have to integrate appropriately accounting for the fact that E is a function of y and z. Okay. Now let us go back to the specific problem that we were interested in, a composite cross section with wood and steel as its components. Now let us see how to evaluate that, how to find y naught for such a composite beam, and how to find this integral E of y minus y naught whole square dAx for the composite beam. Okay.